This video describes a way to identify different format dialects for file formats, even when there's no formal specification, although in this case there will be, using something called the weighted Dowker complex, which is a topological construction that we're going to apply some statistical methods to. This is joint work with a number of people at BAE Systems, and in addition, I'd like to thank Denley Lamb at BAE Systems, as well as my students at data providers and funding source. Now, suppose you have a set of files that supposedly comply with one of several different dialects of a data file format. And you have a set of parsers that read that format and generate a set of messages of some sort for each file. I'm going to describe a situation in which we have a pretty good idea of what the different dialects are, although this kind of methodology works even if you don't know this. What you'd really like to know is there any consensus as to which files comply with the format or not? Do they comply with different dialects? Are the different parsers that are written detecting the same thing, or are they detecting different features? Are there bugs in any given parser? And is the format well specified? Sometimes there are bugs in the specification as well. The key takeaways from this talk is that statistics works very well for ensembles, even if there's an underlying deterministic model. It's perhaps a strange way of putting it, but if you think about it, reading a computer file is an entirely deterministic process, and looking at many different files are deterministic. Where does the statistics come in? It comes in from the fact that format consensus is an ensemble property of the files and the parsers jointly. They work together, and there's some uncertainty. In this talk, I'll give you three different easy-to-use statistical tools. The first is the weighted Dowker complex, which is a very convenient way to cluster files based on the pattern of messages they produce. This gets transformed into a posterior probability for each file being in a particular dialect, and it takes a look at these clusters. And finally, you could do a classification of the files into clusters by way of thresholding this posterior probability. The file format we will focus on in this talk is the PDF format. It's written in effectively plain English. The format specification is not machine parsable, and there's no reference implementation. Although you might imagine Adobe, being the originator of the format, would give you the reference implementation. In fact, Adobe no longer provides a reference implementation, and the format is owned by an independent body. Now, many different parsers will consume PDF files, but they make different choices when the format's ambiguous. When the this is what gives rise to dialects. So when files are not compliant with the format, sometimes the parsers will try to fix the file and continue. That way the user has something to look at. This is what gives rise to dialects. And of course, the parsers themselves have bugs. So the takeaway is, if you're trying to understand whether a file is valid or not, or whether it's part of a given dialect, you really can't trust any individual parser. And an ensemble of parsers is going to be generally more reliable than any single parser. Now, how do you safely test files that might be potentially hazardous in some fashion? By dialect, I could well mean different dialects of malware as opposed to just different benign choices. The tactic is to confine the file and the parser into an environment with very limited input-output access. So some kind of virtualization is a good strategy. The output of this, though, is rather sparse. All you get is a binary relation or a context, formal context, recording which files trigger which messages or regular expressions run on those messages from a very fixed set. So you'll end up with a rectangular binary matrix. The rows are going to be the different messages, and the columns are going to be the different files. You put a 1 if there's a match for the regular expression that detects that message, and a 0 otherwise. It's probably the case that you'll have lots of files and not quite so many messages, but it really doesn't matter. And our working hypothesis is that anomalous files or different dialects will manifest within the context of this relation. For this particular talk, I'm going to use quite a few parsers listed on the slide here, as well as different options that the parsers can be run with. So for instance, you can run mutool with the clean option, with the draw option, or the show option. You get different messages produced as output. For messages, we will capture the standard error output and the return code, and then we apply a battery of regular expressions to the standard error and collect up the matches. As you might imagine, there's a lot of different possibilities here. In total, we end up with just over 3,000 different messages collected. Some of them are duplicates. If you run a parser with different options, sometimes it produces some of the same messages. We have duplicate regular expressions in that case. Here's an example of what some of the regular expressions look like. So they have sometimes they're just it's an exit code that indicates an error, and that's the end of the list. That's not run on standard error per se. But in other cases, there are regular expressions that match standard error. So for instance, various kinds of Caradoc type errors, and you can see the fields in those errors are marked with globs so that you can match. And some of these things are not actually error messages per se, like the message 991 for PDFium processed a certain number of pages. Is that an error? Not really, although the absence of that message could well indicate an error. So the data set that we're looking at is a battery of 200,000 files. Half of them are considered good, half of them are considered bad or invalid. And looking at these are the matrices, so the white or gray is a 0 and colored is a 1. And you can see that the texture of these messages are quite different, or the files are quite different. The 3,000 messages tend not to fire quite so much on the good files, whereas they fire much more frequently on the bad files. You might well say, gosh, all I need to do is count up the error messages and I'm done. Well, to a rough approximation, that's true, although it doesn't give you optimal performance, and it isn't particularly informative about the different dialects. In any case, each column is a distinct file, each row is a distinct regular expression run on a message, on the standard error or exit code. We'll call that in this talk a message. So overall, the workflow that we're going to follow is the matrix that you just saw is the output of this Dowker sandbox, in which every PDF was run against every parser. Of course, this methodology works for arbitrary formats. Just swap out what this parser sandbox is. We're going to take this error matrix, apply the Dowker complex construction to it, a weighted Dowker construction, and do some kind of thresholding based on posterior probability. That'll give us that rock plot is a summary of the posterior probability, and then we can either threshold it or inspect manually to delve into the contents. Okay, so let's talk weighted Dowker. The way that you build the weighted Dowker complex is it's a topological space, an abstract simplicial complex, in which each row of your matrix specifies a vertex, so the A, B, C, D, E vertices. Each column specifies a simplex, by way of indicating which vertices need to be connected. So for instance, if you look at the second column, you will notice that there is a 1 in the A and C rows, so that specifies an edge between the vertices A, C. If you have more than one in a given column, that specifies a higher dimensional simplex. So for instance here, column 4 specifies a triangle by way of highlighting 3 vertices C, D, and E. And of course, you can get some interesting situations where you fail to have a triangle. So there is no column in which there is a 1 in the A, B, C, and D rows, but all the pairs are present. So this indicates that there's some kind of format disagreement that could be potentially present. Indeed, this is an indication of where you might look for dialects. Now, this Dowker complex is quite lossy. It ignores duplicate columns. So here are several different relations that are all quite different. You could definitely say that even if I permute the rows and columns, I can't get one into the other. They're non-isomorphic. Yet they all construct the same Dowker complex. That's a limitation and that's a problem. We can remedy that problem by counting the number of times each simplex appears and labeling the simplices with the counts. So for instance here, the A, C, D simplex occurs 4 times in this particular matrix, so we label it with a 4. Turns out this gives you an isomorphism invariant. So if you have the Dowker complex labeled with weights, you can reverse engineer what the matrix must have been, and vice versa, obviously. But more importantly, this actually this representation is not just lossless. If you enrich it a little bit, keep track of the columns, then you actually end up with functoriality, so that it's structure preserving. How does that work? Well, practically speaking, what you should do is you should display that Dowker complex not as a nice picture, but rather as a partially ordered set. This is a part of the formal concept lattice. And what you do is you put an element in the partial order, which I'm showing on the left of the slide, labeling each column prototype. So for instance, there's an ACD. How do I know that's had to be there? Because I have a simplex ACD, that green triangle, as well as all of its various edges and so on. You put an arrow when you go from, by way of subsetting. So for instance, AC and D points to AC, or AD, or CD, and so on. And what I put in the middle are the labels based on the counts. Now, this is actually relatively easy to compute, so you could do this in a few lines of R, or your favorite language. The tidyverse semantics make it very convenient to express this way. It's just a relatively simple regrouping operation. So that's pretty handy, and starts to suggest that we could do some statistics with these weights. Now, in the PDF data that I've been considering, really turns out there's only two kinds of messages. Those that really happen very frequently, and those that don't. And so what I've plotted here is a histogram of the frequency of the messages, or their probability of occurrence, versus their sorted message number. You can see that there's, in both cases, a fairly steep roll-off. Both of these are shown logarithmically on the horizontal axis, which may feel a little bit misleading, but really isn't. In any case, there's a pretty steep roll-off. So you can kind of divide up, where I've marked vertical gray lines, you could divide up the messages that, to a good approximation, happen pretty frequently versus the messages that don't. And so the tactic should be that you threshold these messages into two classes based on their frequency. And the important observation is these classes differ for different dialects. So you can use the fact that certain messages are much more frequent in order to identify which dialect a given file is part of. You can ask if you think of good and bad files as two separate dialects, do they overlap? Do these messages overlap? Well, what I'm showing on the top of the slide are the 6 most frequent messages in the good files. I've highlighted that region. There they are. Those are the specific ones. You will notice that they occur with probability greater than 50% in some cases, the Caradoc stat strict messages in particular, the message 243. Very frequent, and actually very frequent both in the good and bad files. And although you should, in fact, at that point say, gosh, if they happen that frequently, you should test them for absence rather than presence. In any case, the top 4 of these top 6 messages occur in both the good and bad files, whereas the last 2 are effectively unique to the good files after you check for absence rather than presence. That Caradoc stat strict message basically always happens in bad files and sometimes happens in good files. Okay, so if you follow that insight, you could write a probabilistic model that describes the probability that a given file from dialect A exhibits a set of messages K. So if you think about K as a set of messages and you have various dialects, this is a probability. Probability of message pattern K occurring given that a file is from dialect A. Well, this is relatively straightforward. You just tabulate up the 4 different possibilities, the message did or didn't happen, and whether or not the message is more frequent in dialect A or not. So that's pretty easy. This assumes, however, that everything's independent once you condition on dialect, and hold the thought about the assumption. I am not the sort of statistician who likes to just make random assumptions. I will check them, but hold that thought. The payoff of this kind of model is that you can actually write down a closed form formula for the distribution of message patterns given certain dialects. As I've written on the screen, I won't read it. You can count up how many different possible ways you can get a given message pattern and then tabulate the probability that that will occur. This agrees with the simulated data very well, and even better, it agrees with the practical data very nicely. It agrees very, very nicely for the good files. You can see the red is what the formula gives you. The black is what's actually present in the data in terms of message occurrence. On the other hand, the bad files are pretty good for a while, and then for the very low weight, or i.e. very infrequent message patterns, they diverge. Some of the message patterns that we see are much more frequent in the bad files than the model would suggest. This is indicating a deviation from that independence assumption, and therefore this is a place to look for really interesting files. Where are they? In fact, they end up happen to be localized in a very nice way. So what I've drawn here is the partial order representation of the Dowker complex. Rather than the little cartoons I had on earlier slides, which are kind of small, this is 200,000 files with 3,000 messages. So the Dowker complex is pretty enormous. So what we've done is we've just drawn the partial order. I've left out all the edges so that this isn't quite a mess. And as you go up, you get more messages firing. So the bottom of the diagram is where infrequent messages, or where you get very few messages. That's where most of the good files are, as we imagine. Most of the bad files, and in fact those that really deviate from where the expected counts are, occurs at the top. Pretty cool. There's one little anomaly that happens down near the bottom, where there are some bad files that throw no errors at all, so we can't catch those. Turns out this is because it's actually not good to fail to embed the fonts that you're using, but basically no one checks for this problem. Hint: this is a great place if you want to be a malware author. Okay, well, all right, let's now use this probability. We could use Bayes' rule to threshold and find those probabilities. How does that work? Well, you need to know a few things. Effectively, what you'd like to know is what is the probability that a file is in a given dialect, dialect A, which might be the bad files, given that we see a particular pattern of messages K. Well, we just found, based on our formula, the probability of K given A, the opposite guys. That's the normalized Dowker weight for the bad files. You can either get that from the formula, or you can find it empirically. And you need two other pieces of information. Roughly how many bad files are expected, that's the risk factor, as well as what's the prevalence of the message pattern K in the test data. The prevalence of the message pattern K, no problem, you can find that. The risk factor, you need to make some kind of hedge for that. In our case, we were told what this risk factor was, so we could write down specifically what this particular probability is, and then merely threshold this probability. What's your tolerance? What's your likelihood that you're going to open a file that might be bad, given that you have a certain probability that it is bad? Okay, if you don't do that threshold and you just sweep all of them, you could build a precision recall curve. You want the area under this curve to be maximized, and you definitely do the best if you train using the empirical data to find this probability, the Dowker weight probability. If you don't have any training data, you could still bootstrap using the occurrence of messages, the more and less frequent messages. That's the red curve. And just for comparison, if at the very beginning you looked at this and you said, I'm just going to tune this out because I can obviously tell by message count, well, you suffer performance-wise pretty substantially in that case. Now, why does this work? The reason why this works is because effectively what's happening is you're segmenting the messages into different groups, and that segmenting of messages based on message pattern also segments the files. That's what the probabilistic model tells you. And in fact, for a small Dowker complex, i.e. a very small number of messages and files, or small number of messages, not necessarily files, you can estimate everything that's going on. So here's every possible message pattern for 3 messages. And if you look at it, it turns out that the dialect A files end up on one side, and the dialect B files end up on the other. That's what the little pie charts are showing here. So this gives you some explainability. And part of the reason why this works is because each message pattern isolates a semantic formal concept. I believe, this is a conjecture, that these formal concepts actually align with message ontologies you might create, as in what kind of message is this? Is this a syntax error, a semantic error, or something else? Now, coming back to that independence assumption, how do you test for independence? Well, there's a classic statistical test for this called chi-squared. I teach my freshman stat students how to do this. They wouldn't want to compute the circa 1,000 chi-squared tests, but my computer is no problem. And here is the resulting chi-squared tests for a whole bunch of different message patterns. It's a sample drawn from the 3,000 messages, just as a spot check. Brighter means more independent, darker means less independent. Overall independence holds. You can see that there's some plaid structure. Those come down to duplicate messages deployed with or from parsers that were deployed with different options. So they're really not that independent. Not independent at all. They're quite dependent, but it's really not a problem. Okay, so you do really need a sufficient message diversity for this to work. That's why we have 3,000 messages. So a shout out to Corey Anderson, who built this with the help of Denley Lamb. So thanks, guys. This conditional independence is a starting point. One might ask as a next step, what's the correct measure of message diversity? I've got some hunches for how this might work, and this would be especially important if you don't have ground truth, and it might be visible in the formal concept lattice or in the Dowker complex itself. I suspect a small number of messages are really useful, while the rest are moderately useful, and those moderately useful guys are what really drive your performance. Just to kind of give you an idea what this might be like, overall, it's definitely true. Patterns with more messages are usually less frequent. Here's a histogram that you can see as the number of messages goes up. The weight, or the number of files exhibiting those, goes down. So what you might imagine, though, is that it can't happen the other way. Well, the data actually show quite the opposite. So an inconsistent edge is when the opposite happens. A pair of messages differing by one message. The pattern with more messages actually happens on more files. Under our theoretical model, this never happens. So when it does happen, it is a clear signal that something interesting is happening for those files. And in fact, we can see that in our data. So here are two message patterns I've highlighted. The addition of message 943 triples the number of files that are showing up. Message 943 is an unspecified exit code of origami PDF cop. Don't actually know what it is, but you can make this inference that, hey, it's actually important, and looking at the manual error taxonomy, as in what are the errors typically for these message patterns, they have something to do with compressed streams. So if you happen to get message 943 firing, it's probably an indication that there's some problem with the compressed stream, even though we don't actually see any standard error output. That's pretty neat. So our weighted Dowker pipeline is largely format agnostic. It works on other formats, presumably. In fact, we've tried it on various other formats. We've tried it on CSV files. We've tried it on JPEG files. We've tried it on MPEG files. And it does work provided you have enough features to exploit, i.e. enough different parsers and diversity on their output. What constitutes a feature is a little weird. Could be a lot of things. I list some of them here. But it really doesn't matter if you work statistically. And this thresholding of posterior probability works very well at splitting dialects, identifying valid and invalid files. And it works because it's well justified. If you're interested in reading more about that, here are some references, some software if you're interested, and certainly drop me a line. Thanks.